All right, so you can still see my screen, hopefully.
Yes.
All right, last time we were left with this contribution of the paper. I hope people still remember which paper is this. Stronger generalization bounds for deep nets while a compression approach. And this is indeed after we see, the generalization from a from a perspective using the norms related to the path from input to an output neuron. Now we can see from a compression perspective. Okay, so it's a different perspective. Well, what is the contribution of the paper? Says it's a simple compression framework for proving generalization bounds. Also derive efficient and provable correct algorithm that reduce the effective number of parameters nets. So I think the motivation of this paper really comes from number of parameters or the so-called capacity, how to characterize the capacity of the neural network. And it turns out this paper proposed a very interesting idea of using compression. So if you're able to compress the neural network and somehow still get a very good result in terms of the test accuracy when you use small number of parameters, then that's probably a good way of characterizing the capacity or characterizing the complexity. So this paper combined with margin theory and compression, they're trying to use compression to understand so-called capacity of the neural nets, right? So they're saying, derive efficient and provable correct algorithm that reduce the effective number of parameters in the nets and yielding generalization bounds that are better than naive parameter counting. Actually, I wanted to say that, when this paper came out, people don't have a better than naive parameter accounting essentially, right? So even if it's better, it's of the same order. But there was one pack-based paper, Dan Roy's group, but unfortunately, I don't have time to cover that. Also, I wanted to clarify that the slides that I shared and asked people to read, the paper that I asked people to read about pack-based is also not a non-vacuous bound. But Dan Royal's paper, I can share that paper later, is a non-vacuous pack-based bound. But unfortunately, there is some dependence with the prior, and it is a little bit complicated to understand if you're not very familiar with pack-based. So this is a different approach. This is a compression-based, you know, um, characterization of generalization ability of neural nets. But I wanted to clarify again, this paper is non-vacuous. It's still vacuous, right? So the bound is still vacuous. Can only say that empirically correlate with generalization, but it is not in the order of the generalization error, which is smaller than one, unfortunately. But what this actually, I think the most interesting contribution of this paper is to understand compression. Okay, someone is in the room. Let me do that. Is to understand, generalization through compression. They also say that, it depends on simple, intuitive, and measurable property of the network. Also apply to convolutional networks, which is not necessarily true for a lot of generalization theorems derived before, right? Okay, so this is, the most important slide to understand, preliminary to understand the paper, I think. So is to characterize generalization using compression. What is the first definition? They wanted to define something called gamma S compressible. So gamma is you can think of it as a margin, right? Margin parameter. And S is a sample, right? So your training data set. Now, the gamma S compressible definition is just saying that if you have a classifier, F, right, and GA is the class of classifiers, then we say F is gamma S compressible, while GA, if there exists an A such that for any S we have. So very importantly here, I wanted to emphasize this is for any S within any X within S. It's not for anything else, but only for the data point in the training sample. Okay, so it's x in S. So we have that for all y, fxy minus gaxy, the absolute value difference between the two is smaller than equal to gamma. So, what does this say? It's saying that you can find a GA that is probably, compressed or something, right? Such that this GA can output very similar result to the original neural network. So this fx of y is just the output along the y coordinate. Does this make sense? Okay, well, so this is the gamma S compressible. Also notice that I don't care about other coordinates. I only care about, basically because F, you can think about F as original large neural network, usually is very, powerful, right? The result is usually very good. But now, so if you do some compression, let's say, the compression class is GA. Now, you don't need to worry about all the other coordinates. You only worry about the y coordinate, which is the one usually is correct, right? It's the corresponding one that is corresponding to, is the coordinate that's corresponding to the ground truth label, okay? So that's very important. Now, after this definition of the gamma as compressible, here comes the theorem, which is a very, very simple theorem. Everyone should understand it immediately after you see this, because we've learned about margin generalization error before. So what is this? This is saying, suppose GAS, where A is a set of Q parameters, each of which can have at most R discrete values. So this is characterizing GA, okay? Before we're saying, the gamma S compressible is with respect to such a GA class, but now let's characterize GA. Let's characterize GAS as something like, GAS for any A, where A is a set of Q parameters. So how to understand it in English? You're basically saying, I have a small network, right? A compressed network, which has Q parameters. Here, it doesn't say anything about small, but I'm just interpreting it as small. Q can be even larger than the original number of parameters, but let's say you have Q parameters. And the Q parameters each have at most R discrete values. So what does this mean? The number of, if you even enumerate all possible ways of, values the parameters can take, how many can you imagine? It's finite at least, right? It is not a continuous variable, continuous space. It's a discrete space. It is finite, although it might be still bad because, so, can someone tell me how many values for a set of Q parameters, each of which have at most R discrete values? What is the total number of possible values you can imagine? Okay, someone says R to the S, someone says Q to the R. Anyone wanted to say which one is correct, which one is not? R to the Q, okay. So it's either Q to the R or a Q power R or R power Q. Which one's better? Which one is right? Yeah, exactly. Yeah, because you have at most R discrete values, right? And you have Q parameters, so it is R to power Q, right? So, but nonetheless, it is going to be something, although it's exponential in terms of Q, it's very bad, but, we'll see. Finally, the result is kind of very surprising, right? So let S be a training set with M samples. If the trained classifier is gamma S compressible while GAS, with helper string S, then there exists A with high probability over the training set that we have this generalization bound. What is this generalization bound? L0 of GA is nothing but actually, so we didn't define what is 0, but basically it's just like we're saying is a normal classification error kind of thing, 0, 1 error kind of thing, right? So you can think of it as just like the true error of the GA, okay? So, just like R of GA, like what we were used to, the notation. We usually use capital R to denote the expected error. Now this is L0 of GA. 0 only means that I am not penalizing for, high confidence or something. So, we'll talk about that later. Anyway, so this is L0 of GA, smaller than equal to L hat gamma of F. So this L hat gamma of F is very interesting. First of all, this is L hat. So that means it's an empirical error. Okay, so it is not it is something evaluated on S. Okay, let's put it that way. Now, what is gamma? Gamma means that not only you have to be correct, but you have to be correct by a margin, gamma. All right, so if your largest value, look at the logist, like if your largest logist is not gamma greater than the second largest, you still get penalized. Just like our margin loss function. Do you remember our margin loss function when we introduced margin? So this is exactly something related to like margin loss function. You penalize by not having high confidence that although you are correct, but you're not very confident, I'm still gonna penalize you for a little bit, okay? So this is L hat gamma F. Now, very interestingly, you can see is the square root of logarithm R to power Q. So it becomes Q logarithm R. You're taking a logarithm with respect to the total number of parameters, okay? And then divided by M. What does this remind you? What does this remind you? Think about the finite, is that Rademacher complexity? Well, think about the finite hypothesis, right? This is a finite hypothesis scenario. Does this remind you of the finite H? Yeah, cardinality of H, logarithm or cardinality of H? Exactly, right? That's why I'm asking how many possible values you can, for all these Q parameters can take is R to power Q. And that's why taking logarithm R to power Q is just Q logarithm of R, okay? So this is exactly logarithm of cardinality of H, which is now why I say everyone should be familiar with this result, right? Okay, so this is a very interesting result. This theorem says that, you have this generalization bound related to margin, but also related to after compression, the complexity of the hypothesis class, right? So I don't have, so unfortunately, Jonathan, you were asking about the helper string. I don't have time to talk about that now, but we can talk about that offline. It's not as important right here, but it's kind of something related to, for example, the specific compression mechanism you're using. And in this paper, I believe it refers to some kind of random, matrix projection stuff. So we don't have time to talk about it, unfortunately, now. But that's a good question, though. Okay. So now the idea of compression. I'm stealing Benham's slide here. So what is the idea they were saying? So you have an FAX. Okay, so this is like a you have an input and you have output from that neural network. Is a very large neural network. It's deep and it's wide. It's wide and it's deep. But now what you can do is you can somehow compress it. For instance, this is how you're compressing this specific layer here, okay? So once you get the compression, what can you expect? For those of you who are familiar with, you know, for those of you who are familiar with the, some of you've learned about signal processing or information loss and these kind of concepts. If you have a compression, what do you expect? You know, I'm saying I have 100 million parameters in this layer to do a function transformation. You said, no, I just need 100 parameters. So I would say you might get a loss, right? Like a noise, right? So by compression, you kind of suffer from noise because I believe that my network is very good. Why? Because my network, although it's large, it has a good generalization error. You know, training error is 0, generalization error is like, you know, 2% or something. So I'm very happy about my network. But you just told me, you know, you wanted to do compression, you'd reduce my number, you know, 100,000 parameter to just 100. So I would tell you, no, you might suffer from noise, right? From my perspective. So that's why they're talking about compression and noise stability. What does that mean? It means that basically, if you wanted to understand compression's effect on the network, you can kind of get this by injecting noise. Do you agree? Right, because effectively, if I add noise to my network, it might be that this noise is very related to if I do compression, I would also suffer from noise. So if I understand, you know, the noise effect in my network, then I hopefully can understand how I can do compression, right? That's the motivation here. And that's why they were choosing to add noise, okay? So after adding the noise, now you wanted to understand how does the noise propagate with network? And in this scenario, you wanted to understand in the upper part of this network, the top part of this network, the thing that's, you know, that's shaded, how would the noise, you know, what is the effect of this noise? Okay. So that's why they say, oh, right. I guess, you know, this is a little bit confusing. You know, Laura's asking, I don't understand why they would introduce noise if compression introduces noise already. I think, you know, the way the figure might be a little bit misleading, but what it is really trying to say is that compression is effectively like adding noise. Not like, you know, I do compression and also add noise, you know, is just the way that they're thinking that how they can analyze the stability or noise stability and effectively understanding compression, okay? So they have this data dependent properties. They're saying that the properties that cause the noise stability or cause the instability of the noise are mostly the 4 different aspects here. So one is the layer cushion, there is the interlayer cushion, activation, contraction, and interlayer smoothness. But, you know, we were not going to talk about it now, but in the next few slides. But these 4 properties are essentially something that characterize how I will behave according to some noise. So effectively, I'm trying to understand if I do some compression and I suffer from some noise, how would I behave, right? So that's essentially the idea of this paper, right? So you can see this figure here, this noise stability of deep networks. This is the figure 1 from that paper. You can see this is attenuation of injected noise on a VGG19 network trained on CFR10. And the x-axis is the index of the layer, and y-axis is the relative error due to the noise. So you can see, you know, what you can see here, right? It says that the curve starting from layer where scaled Gaussian noise injected to an input. So it is very interesting, right? It is analyzing some Gaussian noise. But of course, like I said in the previous slide, you know, I don't know whether my compression would render a Gaussian noise or not. So this analysis is only, showing how, if you add a Gaussian noise, how does the network react to these Gaussian noises at different layers. But I haven't really understand how my compression would work yet, because by doing compression, I do not necessarily render Gaussian noise. Does that make sense? Okay, so now a curve starting at the layer where a scaled Gaussian noise is injected to the input, while L2 norm is set to be 10% of the norm of the original input. As it propagates up, the inject noise has abruptly decreasing effect on higher layers. So this is very important. So what does this mean? It means that the injected noise has rapidly decreasing effect on higher layers. So if I inject noise down there, my higher layers won't be affected much. So that means I have potential to compress my lower level of layers. Agree? Although there is a caveat here, I'm studying Gaussian noise. Questions? Okay. Okay. All right, so now there's this definition 3. What is it saying? It's saying like F is a mapping from a real value vector to real valued vector, and N is some noise distribution. The noise sensitivity of M at X with respect to N is defined as the following. So this is noise sensibility. You can see this is like, the first is the L2 norm squared difference between adding the noise versus not adding the noise. Okay. So you can see how much noise you're adding. You're essentially adding epsilon multiplied with the L2 norm of the X here. Okay. Okay, so once you define that, then you have this proposition. This proposition is saying, right? So like if a vector is, so let's first understand this proposition. The noise sensitivity of a matrix at any vector x not equals to 0 with respect to Gaussian distribution is exactly here. It's the Frobenius norm of the M squared and L2 norm of the X squared divided by M X L2 norm squared. So this is very interesting, right? What does this imply? The proof is right here. I don't want to go through it. You can look at it. But I also expect that everyone has now so far read the paper. So what does this mean? Right? We already have it here. It means that if a vector is aligned to a matrix, okay, which is basically means that it is correlated with high singular directions of M, then matrix M becomes less sensitive to noise. Okay, so this is very intuitive, but because you can think about matrix as a linear operation, but doing like an affine transformation along mostly the singular directions, right? So doing an amplifying of the directions along the singular directions. So if you have a stronger amplifying, and if the vector is like aligned to a matrix correlated highly with the high singular directions of M, then matrix is less sensitive to noise at X. Okay, so based on this observation, this paper says that we're going to compress each layer by an appropriate randomized compression algorithm such that the noise divided by noise error ratio in its output is Gaussian-like. Okay, so this proposition is only for Gaussian. So that's why it's saying noise error in its output is Gaussian-like if layer I+1 and higher have low sensitivity to this new noise, then the compression can be more extreme, produce much higher noise. Does that make sense?
Could you rephrase that last sentence, like after the comma?
Let me see. I cannot hear you very well. Can you say that again?
Could you rephrase the last sentence right after the comma? So then the compression, like, can you just say that differently?
Oh, they're saying that if layer I+1 and higher have low sensitivity to this new noise, then you are able to add more noise, and therefore have more extreme compression.
Got it.
Yeah.
Thank you.
Does that make sense? Okay. Well, if no questions, we can look forward. Look ahead. So now we wanted to introduce this four properties introduced by this paper that are effectively. Okay, let's go back to the slide. The property that cause noise stability. So the four properties that are most important for characterizing the noise stability. So what are the four properties? The first is the layer cushion. So you can say basically is the alignment of layer input to its weight. So this is actually also a slide stolen from Benham, but so you can see the first one is the WX norm divided by norm of W and norm of X. So this is like an alignment of layer input to its weight. Okay, that's very easy to understand. Now, the second one is the interlayer cushion. Interlayer cushion is alignment of layer input to Jacobian, right? So if you have a Jacobian, okay, so your fx is essentially this thing, right? So it's like the gradient xf and x. So if you look at the alignment of layer input to the Jacobian, again, is just like, the norm of the multiplication divided by each one of them, the norm of each one of them. So that's the second property, interlayer cushion. So they call it interlayer cushion. Now, there's also this interlayer smoothness. So it is not, it's not something that they put a math equations here, but you can probably refer to the paper. But it's basically saying is the deviation from a linear approximation. So this is very related to the smoothness definition in optimization. Okay, so they call that interlayer smoothness. It is related but not the same to the optimization, the usual smoothness parameter in optimization. But this is nothing but a deviation from a linear approximation. Now, the fourth property is the activation contraction. And this is actually very interesting. This is almost like saying some kind of Lipschitz kind of contraction. They call it activation contraction. I think it's more accurate, maybe that way. So it's the ratio of the norm before to after activation, right? So you know that before activation is Z, but after activation is gonna be like a Raoult activation. So anything smaller than 0 is 0, anything greater than 0 is itself. So it becomes Z plus the bracket plus, and then L2 norm. So they're just measuring the difference, the ratio of the norm before and after activation. So the denominator is C. Okay, so these are the most important properties to characterize the noise stability. So they have a formalization of these error-resilience. In fact, they were just defining these in a more formal way, like layer cushion, interlayer cushion, activation contraction, and interlayer smoothness. Okay, so mathematically, if you wanted a formal definition, here is this definition. Okay, so let me pause for a second in case there is any question. Michael has a very good question, and I think it's very, very important for our understanding. Michael is asking, do these results allow one to say anything at all about generalization of the original F or only the compressed G? Actually, I think that's worth discussion. I have my answer. I don't want to say it now, but I think it's worth for us to have a discussion. Do you want to, speak any of your, your comments to this question? You
To
can.
me, it seems like no, but I could be wrong about that. That's why I'm asking.
You believe this is the compression, this is the generalization for the compressed G, right?
Yeah.
Okay. Yeah. Anyone else? Any objections or other thoughts? Or why are we characterizing the generalization of the compressed G? That's a very good point. Don't be shy, guys. Anyone wanted to say anything? Yeah, so someone says, I think it's a yes, since loss can't do much on G, so F would be the same as generalization. Do you?
So there's probably some bound relating the two generalization errors.
Is there?
I don't know, I suppose. I think intuitively, because G kind of approximates F within a certain error, but yeah, don't really know.
Right, so this is actually a philosophical question, I would say. This is the whole idea of this paper. I think is the biggest contribution of this paper also, is to say that in order to characterize the generalization ability of a large network, you don't want it to look at itself. You want it to somehow find its compression and then characterizing the generalization error of that compressed network. And as long as the compressed network has a good generalization, this is a good characterization of the capacity of that big network. Right? So this this compressed network has to be very close to the large network on the sample. Right? Remember that gamma S compressibility. It has to be very close to the large network on the sample itself. Of course, not on anything else, but only on the sample, on the ME examples you observe. So that's kind of a restricting, kind of putting a restriction to the compressed network, right? You cannot get arbitrarily small network and claim that is a compressed version of my network. You cannot do that. You have to making sure that this network somehow performs very well on this training data set, okay? And after you do that, then this paper is saying that I don't want it to directly characterize the generalization of my large network. Instead, I wanted to somehow characterize the capacity of that large network through this generalization error of the compressed network. And that's the biggest contribution of this paper. I think they are trying to do that in a very different way than the previous approaches, because the previous approaches are all trying to characterize directly on the large network, the generalization of the large network. And what this paper is saying, I don't want it to do that. Let me just characterize the generalization error of the compressed network. So let me go back to this again. This is very important. So so this theorem 2.1, it is the most important theorem in this paper. Of course, this is not the main theory of this paper, but I think this is the philosophy that we can learn from this paper. It's saying the L0 of GA, so it's the expected error or the generalization error. It's not the gap, right? The generalization error of the GA, which is the compressed one, which is the one that is resulting from this gamma S compression. So what does this mean? This means that this paper is trying to transfer the difficulty of characterizing the complexity of the hypothesis class into characterizing the complexity of a compressed hypothesis class. So before we were saying that hypothesis class was very, very difficult to characterize because it's, exponential in terms of depth or polynomial in terms of, number of parameters or so. So the complexity is just too high, right? You cannot make it non-vacuous. The bound is always vacuous. But now we're saying we don't want it to do that. It's just difficult. Let's just think about a new way. Let's just think about characterizing the complexity of a compressed network. And you can see that's why we're looking at the cardinality of H, and the H is essentially the compressed one, not the original one. Okay? So that's why it's it's very philosophical. So Michael is saying, so philosophically, generalization of G tells you something about F, but there is no way to get an explicit bound for L0F, and I think that's correct. And that's what they were trying to say, that you should use G rather than F to characterize the generalization ability of F. So Laura is asking, I guess the takeaway is that we aren't making any claims on generalization of F, but rather just something else that is close to the origin F. But I actually don't agree with that. I think what they were trying to say is that the right way to characterize the generalization of F is through this compressed GA. That's what they were claiming. Yeah. Okay, this is a good discussion. I like it. I didn't emphasize this very much. I thought by looking at the theorem 2.1 is obvious, but no, this is a good discussion. Any other questions or comments?
Yeah, is it fair to say that even if G and F behave similarly on, say, the training data, they may still behave really differently on the entire distribution?
Yeah, true. And now, however, remember what we were talking about on Kenji, the last paper, Kenji's paper on, I don't remember the title of the paper, but the second paper we talked, right? Everyone knows what it is. So they're talking about a point, P, X, Y, and S. Okay, remember that? So, a lot of generalization, statistical learning theory was trying to characterize a set of PS, right? PS is a tuple, is a pair. So you're just studying the learning theory is trying to characterize a pair of PS. Here, you are still trying to consider, the underlying distribution somehow, because I'll talk about that later. But the improvement from this paper is to consider a specific S rather than a set S.
I see.
Yeah, it is still somehow considering any underlying distribution. Why? Because Kenji's result has a expectation. Remember when we talk about that final theorem 7 last time? Kenji's result has this expectation over Z. And how do you get that? That expectation depends on the specific PXY, the underlying distribution. Remember? However, here, we're not doing that. We're not explicitly putting the bound as something that has to be evaluated using the underlying distribution. we're still using a set. However, we're specifically looking at a sample S rather than a set of S. That's the major difference here. And that's why I think is a very interesting result we should be looking at using compression. So it's a nice way of transferring the complexity through the complexity of the compressed one, but the compressed one is related to the specific S that we're looking at.
So maybe, like, yes, just because F and G behave similarly on S does not tell us that they'll behave similarly on the rest of it, but also as S becomes, say, better and bigger and more representative of the entire distribution, maybe F and G will behave more similarly as we look at the entire distribution.
Right, so I don't have an answer for that, but I think that's a very good point. I think it's kind of a little bit hard to understand what this is really trying to say, but overall what they were trying to say is that they were not trying to characterize, they don't want to comment on whether F or G would behave very well on the entire, on anything that's drawn from that distribution. I think they're not explicitly trying to connect the generalization error of F and GA, but rather they wanted to claim that the GA should, maybe they were just implying that. They were just saying that GA should be the right thing to look at when you characterize the capacity of the F. But maybe that's implying kind of the generalization ability of these two are very similar.
Okay, thank you.
Yeah, I don't know the answer to that. Yeah, don't quote me on that. I don't want it to, mislead anyone. Okay. So this is the generalization bound. The theorem, so let's see, what is this saying? The theorem is that it's saying the capacity is proportional to the depth multiplied with the activation contraction divided by layer cushion multiplied with the interlayer cushion. Okay, so this is like the noise resilience, right? So they were basically finally figured out a way how the noise, so the previous properties, how it is related to the generalization, and that's the theorem. And essentially, what this paper says that it is much better than parameter counting because you can have a very good compression of the network, and the capacity. So you can see this is the so-called capacity comparison. It's basically like the bound that they're comparing. You can see the number of parameters is this red dash line here. And this paper seems to have a better result than just purely computing number of parameters, whereas many of the previous papers characterizing generalization was worse than the number of parameters calculated, just counting the number of parameters. Okay. So also they say we identified data-dependent property that cause noise stability. What is data-dependent here? They were referring to S, right? They were trying to say that the compressed one is dependent on this S only. So that's a data-dependent property. Also, there's this data-dependent properties, which is also like these properties are evaluated on this S only. So here, all these are evaluated on this S, X, and X is from that S, your sample. So this is so-called data-dependent properties. Okay, and indeed, they were able to distinguish like the normal data versus the corrupted data, as we see from the first paper we read, right? We have like the corrupted data or the random test versus just the natural data. And they can see like two peaks very separately from each other by looking at this random data versus the crop data. You can see these data-dependent properties actually, are very different between the normal one and the corrupted one. So what this is saying is basically the paper claims that they find some properties of the data such that it distinguishes the normal data from the corrupted data. Okay, so that's what they were trying to say. And they were saying that these properties are kind of interpretable, right? You can, by looking at these properties, you know whether this is normal data or corrupted data. Okay, so this is the final generalization bound. What is it? Is for a theorem 4.1 for a fully connected network. Of course, they also work for convolutional nets, but I don't have that result put here. You can refer to the paper. For fully connected network, and with probability delta and any margin gamma. Again, this is the margin theory, so gamma is still there. Algorithm 1 generates weight. So we'll see what is the algorithm 1, but it's a compression algorithm. You can think about it as matrix projection. We'll talk about it in a second. So algorithm 1 generate weights A tilde for the network. Therefore, you get a compressed network F A tilde, such that with probability, with high probability, right, 1 minus delta, over the training set. And F A tilde, the expected error of F A tilde. So this is the generalization error of this compressed one is upper bounded by this thing. Okay, so this is the empirical margin loss plus this term. So you can see this term has now been replaced. So before we can see theorem 2.1, let's go back there. You can see here, this is Q logarithm of R. This is like been, before it was the cardinality of H, right? So now they figured out under algorithm 1, what would that be? How much number of parameters you would need in order to have a gamma. Okay, gamma as compressible. So basically, this is the number of parameters. So you can see here, but also it depends on these properties we've defined before. So the 4 properties which are evaluated using the data-dependent evaluation. We can evaluate these 4 properties. Essentially, it becomes this term. Okay, I don't want to go into the details right now, but you can take a look at it in more detail. Now, what is this algorithm? This algorithm. So now before we go to the algorithm, I just wanted to make a comment here. We look at a generalization error, right? So we look at how a generalization of a compressed network can be guaranteed. Also, from another perspective, guys, the question that we were asking before, why do I characterize the generalization error of a compressed network, is that compression is often desirable. Why? In this, in today's machine learning, many people wanted to personalize machine learning. You wanted to do like learning on your phone, learning on your your camera with some computation power and something like that. So you really want small networks, right? You don't want large networks because you can only run those on your powerful GPU clusters or something like that. So for ordinary people who wanted to use machine learning to do something simpler, you wanted to, or even to do something complex, can we hope to do some compression, right? And this is very important because if you have a small network, think about how you use a neural network, right? For training, it's fine. You can just do one-time training and that's it. You don't need to do anything else more than just the training. And once you have that network, you can just, whenever you have new examples coming in, you can just do a forward pass and get the result, get the prediction, or do the inference. You get the result. But what's the caveat here? The caveat is that if your network is really large, every time when you need to do an inference, when you need to do a prediction, it's going to be very expensive because your network is just very large. And that's why you wanted to do the compression. You want to make sure that a network that is compressed still have a very good generalization ability. And that's why this paper is very powerful, because it's saying that if there is some small, if my small network performs very well on a specific sample, then the generalization is also guaranteed for that small network. Wasn't this very powerful? This is very powerful. This is saying that I can get good generalization as well as good a compression, right? Does that make sense? So that's why this result is very, when I saw this result, I was very inspired and I was very excited about this result. Okay. So I wanted to emphasize again. So Michael is asking, do we know approximately what QR are for the real types of compression people want to use? I want to say it's not necessarily, this paper is not focusing on Q and R, but rather this paper is saying, through this specific compression algorithm, you can get some properties of the network, and essentially that properties of the network would be the final generalization gap. Okay, of course you can use theorem 2.1, which is fine, but this paper is taking that forward, right? It is even better than 2.1, theorem 2.1. Does that make sense? So what this paper is saying is it relates to, we propose 4 properties, and the final one is just relating to these 4 properties of this network. And now let's look at this let's look at this matrix projection. Okay, so what is this saying? It's saying that we have some random matrices. So this is a fully connected neural network. Remember the complexity of the fully connected neural network are just the matrices for each layer, right? You have matrices, they have a ReLU and so on, but the complexity really comes with the matrices. So what this paper is doing is that you have some basis matrices. So M1 through MK. What are these basis matrices? They are called helper streams. So these basis matrices are the entries with either +1 or -1. So they're random matrices. So once you have K such random matrices, you can just project your matrix. So let's say you have a matrix A, okay? You can write that in terms of summation of, let's say, alpha I. I'm not using their notation here. Let me just use my own notation. Any matrix can be written as a linear combination of these basis matrices, MIs, I from 1 to K, okay? Of course, you might have an error depending on the K here, right? If K is really large, then your error is smaller or 0. But if K is smaller, then this becomes an approximation. It would render some noise. And that's how we call it compression. Like we would get some loss. We would render some noise. Does that make sense? Any questions so far? Okay, so now, for each network, for each layer, you would have such a matrix that can be projected into these coefficients. So what does that mean? That means if you somehow just have a common constant, you have a consensus of what are the MIs, what are the basis random matrices, then I only need to store the alpha i's, right, for a layer. Before it was a gigantic matrix, but now I only need to store these alpha i's, alpha 1, alpha 2, alpha k. to completely characterize this layer. Do you see? So that's why we say this is a compression, because before I have to store every element in my A, but now I can just store these alphas from alpha 1 to alpha k. Does that make sense? So now I'm going to ask you, first of all, what is my memory cost? Let's say if I store all the k m1 through mks, if I do that, and let's say k is even greater than the depth of the neural network, then my memory requirements is even higher. Do you agree? And but is there any get around? I don't have to store all these MIs. I can just store the random seed, right? I mean, I'm using a random seed to generate my MI to MK. If I don't store them, I can just use a random seed. Now, all I have to do is to store this random seed and these alphas. Okay? Now the question is, what is the overhead? Is there a free lunch? No, there is no free lunch. The overhead is that you have to compute this MI through MKs every time when you are trying to do a forward pass or a backward pass. And also you have to reconstruct your A through this linear combination of these MK bases. Any questions? So that's the caveat here, right? You can either save computation through compromise on memory, or you could save memory by doing more computation. But either way, there is a compromise. You don't, get both. And that's essentially the drawback of this paper. The compression mechanism doesn't seem to be very practical. I don't have other things to say here, but any questions? So indeed, I wanted to say that we have my group has a paper on this, which is proposing a new architecture design using tensors. We will learn tensors later on in this class, but we might even spend some time talking about that paper. But the idea is that we can use a new architecture design, and we can also get like a compression method using tensor representations. Essentially, it's much more practical than this matrix projection. You save a lot of computation, and you're also able to achieve very good generalization, sometimes even generalization improvement. You're also using higher order statistics, which is sometimes better than using lower order statistics, because the higher order statistics is more prone to low rankness. So essentially, you need only small number of factors to have a very good approximation of the original data, or the original data matrix or original weight of the neural network. So essentially, we kind of extend this work to have a more practical compression mechanism. And the generalization is also improved from this paper. I don't have time to cover it, but if you're interested, feel free to look at our paper. Okay, so any questions? I don't have time to cover this pack-based approach, unfortunately. And also I plan to, I think this paper is a more interesting paper than this one our original planned to do. So if you are interested in pack-based, please take a look at this paper. Okay, so this is a much more interesting paper. Okay, so any questions? If no questions, I'm gonna move on to defending against adversarial perturbations. I won't have time to cover everything I plan to cover, but I will introduce the most basic concepts and we will talk into more details next time, okay? So we've talked about generalization, right? So we started with generalization learning theory. And those learning theories were not really designed to work for deep neural networks. But nonetheless, people have spent a lot of effort trying to use the learning theory to understand generalization in deep learning. And one of them I'm personally most excited about is using compression, because the compression is really something we will need for modern machine learning to have federated learning or personalized machine learning. And having a guarantee on the generalization of the compressed network is very powerful. But nonetheless, we are talking about everything which is, everything you've talked about so far is assuming that data are coming from the underlying distribution that is the same, right? So you have an underlying distribution on the X and Y, the input and the feature space and the label space. But in practice, if you consider the security of neural networks, it is not necessarily true. And that's why people are talking about the robustness of neural network. So it's essentially doing perturbations of the input or poisoning of the input. Also kind of, you can also think about poisoning some of them as perturbation. You might suffer catastrophic failure from these perturbations, from these adversarial behaviors. So from these adversarial input perturbations. So I wanted to spend maybe 2 lectures to talk about these issues. I didn't have this before in last year's lecture, but I think now it's getting more and more, attention, and maybe we should spend some time talking about it. Now, I call this adversarial, defending against adversarial perturbation. As you can see, I don't specify whether this is training time or test time, but let's first see, you have an attacker that may inject malicious data to poison the learning process or manipulate the data at a test time to evade detection, okay? So we're covering both the poisoning and the test time evasion, right? So these kind of attack have been reported against antivirus engines, anti-spam filters, and systems aimed to detect fake profiles or news in social media. So it's widely applicable, and it's concerning our everyday life, because machine learning is being used in a lot more, increasingly more and more applications. So we care a lot about the security. And all problem involving a well-corrected deployment of machine learning algorithms. So let's first see adversary examples. Everyone has seen this. I don't want to spend too much time on this. So examples that are misclassified with high confidence. So these are adversary examples. Only have been slightly perturbed usually, right? You could imagine you have like, there are misclassified using different classification models. You have targeted ones misclassified to a given target, or non-targeted ones just misclassified to any incorrect class. And indeed, the way how you perturb the data could be very different. Sometimes you could just do a function transformation, such as tune the tone of the image, or you could do an LP norm perturbation. So, mathematically, it is well understood using LP norm perturbations. Although it has not been proven that humans are, LP norms are imperceptible to humans, right? So, or you could also consider wearing, or like patch kind of attack. By that I mean wearing a hat, or wearing a sunglass, or wearing some kind of special glasses, right? For example, here, this is the special glasses that you're wearing here. Okay, somehow you could classify this woman as someone else, who is another celebrity. Okay. So the types of attacks are, I would say, broadly divided into two categories: poisoning and adversarial examples. So poison happens at training time, right? You can basically, how you care about poisoning is we make this assumption that you can control input during training time. Actually, later on, we'll see the two scenarios that a system is really susceptible to poisoning. Now, adversarial examples usually happen at test time. It's making an assumption that you can control inputs during test time, and people, can think anyone who are trying to get a test label after using a trained model could potentially manipulate the input images, so that this means that you can control input. The adversary can control inputs during test time. So first of all, we wanted to talk about poisoning, right? So a coordinated attack in which a fraction of the training data is controlled by the attacker and manipulated to support the learning process. So this is somewhat a formal kind of English description of what is the poisoning. So why do we do poisoning? Sometimes, people might say you cannot always control inputs, or you can always control target, right? So often in a lot of scenarios, you have to learn the machine learning algorithm, right? So how do you learn the machine learning algorithm? In our academic scenario situation, usually you have this benchmark data sets, right? So CFAR10 and NIST or ImageNet. But in practice, you don't have these benchmark data sets. You somehow have to collect your data. And people are familiar with crowdsourcing, right? People often just crawl data from the internet, or, okay, so I'll stop right after I finish introducing the slide. People sometimes crawl data from the internet, or people could also think about, trying to collect data when you interact with your users, right? So you cannot control how your inputs are, accessed, right? You cannot control them. Sometimes people would have this adversarial inputs that can poison your entire learning system. Also, you cannot control targets, right? So sometimes, you would have very strange, stuff for like phishing emails or competitor emails. They could just completely poison your email, the systems that prevent phishing emails in your system, if you're using a machine learning algorithm. So overall, this is like some motivation of poisoning. But later on, after today's lecture, later on, we will see, I wanted to give a very brief, preview of next lecture. I will talk about how poisoning works. I will also talk about, some poison attacks. I will talk about a formal definition of a formal poisoning attack, but all of these I will go through very quickly. I will talk about a formal framework for poisoning attack. I will also very quickly talk about poisoning defense. I don't want to spend as much time on adversary examples than poisoning, because I think adversary examples, most of you are more familiar with that. So I wanted to very quickly go through some certified defense for adversary example. I want to go through the attacking methods such as PGD attacks or something like that. I think those are too basic. So it goes through some of certified defense, and that's basically our plan for this robustness of neural networks. Okay, all right. So that's it for today. Thanks everyone.